Thank you. You are being placed into conference in muted mode.
During the last year, we served over 6,000 individuals, CAD tools from 30 different suppliers and 70 different packages. We helped researchers and industry prototype and design over 350 individual projects in 25 fabrication technologies, from global technologies to best-in-class here at home, such as the Teledyne DALSA processes. We offer training courses, workshops, and events throughout the course of the year on the latest CAD tools and technology offerings. And last but not least, as important, we sponsor and participate in joint industry, academic, and CMC projects. Next slide. And my last slide here, CMC is really about making things. From design through manufacturing, we have capabilities and skills through our partners in photonics, microelectronics, MEMS, microfluidics, and embedded systems. In addition to offering these technologies from leading Canadian sources, such as Teledyne DALSA and international companies, we also offer unparalleled knowledge and access to Canadian government, not-for-profit, and university fabrication and lab facilities. We have over 30 engineers to provide you a substantial support in accessing the technologies, understanding your requirements, tools, and training. And we also work to lower your research costs, whether on the academic side of things, from supporting you directly with NSERC dollars, to consolidation of demand and leveraging the national scope of the NDN to bring you the lowest overall cost to get your research work done. So again, I just want to say how happy we are to be working with Teledyne DALSA to help bring this MIDIS platform into the marketplace. Thank you very much. Luke?
Yes. Can you hear me?
Yes, we can.
Okay, very good. I will share the see it?
Yes, we can see.
Good. So I'm happy to be here talking this webinar about our MIDI platform. So again, I'm Luc Ouellette, VP Technology Development here at Teledyne DALSA. So what I will share to you is, first I will present Teledyne DALSA for the ones who do not know. Then I will share with you the MEMS and inertial sensor expertise. Then I will introduce MIDI. Then I will open, okay, the next portion of this communication openly to introduce CMC. Then I will show what will become MIDI also, the shrink of MIDI, the wafer level integration of MIDI to CMOS, and future integration into MIDI. So as for you to understand that this is a very serious platform for Teledyne DALSA, and it will grow and it will expand. So any effort on this platform will probably be very fruitful in the future. So first, Teledyne DALSA. We do foundry service for more than 30 years. We used to be a mixed signal CMOS, but we developed CCD and MEMS expertise, and we are leader in these markets. We do pure play foundry for MEMS, both on 6 and 8-inch wafer. We can accommodate low and high volume. We have a world-class quality system. We are TS for automotive and ISO 14001 for environmental control. We are qualified automotive supplier. So your project on inertial sensor is the target automotive, no issue. We are audited by major automakers. In fact, we're audited by another tier 1 supplier last week. And we have reliability testing monitoring, and we do failure analysis. Can you still hear me?
Yes, we can.
Very good. So we are the #1 pure play foundry in the world. In April 2013, last April, okay, we were in fact quoted Teledyne DALSA pure play MEMS foundry shoulder to shoulder with TSMC. So it's important to know that here in Canada we do good technology, particularly in the field of MEMS, and we give you access through this CMC. The kind of MEMS that we've done in the past, inkjet printhead, pressure sensor, microphone, accelerometers, gyros, and the remaining of that list. So we are very diversified in the fabrication of MEMS and the mass production of MEMS. In the field of inertial sensor, we do inertial sensors since 2002. We did develop and mass-produce gyroscope, accelerometers. We've served many customers, including InvenSense, that became very famous, growing the inertial sensor business, initially through Teledyne DALSA, and after that with Asian foundries. So we are targeting many markets: gaming, image stabilization cameras, portable device, automotive, so the kind of thing that our teenagers have in their hands, basically. We've shipped more than 100 million units. In fact, and this number is still growing very fast. And now we introduce a platform, a standard platform based on these 11 years of inertial sensors expertise, and this is MIDIS. So what is it that differentiates MIDIS? First, it will grow very, very small dies. The dies are small. Okay? Those dies are even more shrinking because there will be a reduction of die size with more aggressive lithography. I will talk about that. Smaller die size are also accomplished via through-silicon via technologies. I will explain. We target to combine gyros and accelerometer on a single chip, meaning two independent pressure on the same chip. So very low vacuum, very high vacuum for gyros, Q factor, and an optimum damping for accelerometer. SOI eliminated. We only use single-side polish and double-side polish wafer to target low-cost consumer electronic product. Getter is also eliminated. So double direct wafer bonding while maintaining good Q factor. Gold is also eliminated, and we still have hermetic direct wafer bonding technology. And thick silicon via epitaxy is also eliminated. We use standard silicon. So these are the ingredients for low-cost introduction of inertial sensors into consumer electronics. And aside that, we will push in the future CMOS MEMS integration. We have activities in that, and I will show you what we're doing. So MIDIS is very, very popular. It's popular here in Canada. In fact, they are a startup created here in Canada to exploit MIDIS. I cannot disclose the name, but there is a startup here in Canada. We're also very, very used in USA. We also deliver in Japan, we deliver in Korea, and we deliver in China. Very few companies here in Canada and elsewhere in the world can pretend that they produce the machine they fabricate for Chinese. We do. Okay? So there's something in MIDIS which is very cool. Okay? It's offered. It's a proven process. We offer a design kit, and it's already used all around the world. So this high-performance platform is based on the integration of gyroscope with Q factor way above 10,000. Of course, this is design dependent on the anchor, depend on the many things, but basically we demonstrated Q factor above 50,000 without getter. Accelerometers typically sealed at around sub-atmospheric condition, around 20 kilopascal, for efficient damping. Again, this is design dependent. Optimum damping is design dependent. And we have the antechamber concept, where no gas contamination from the atmosphere from the accelerometer cavity leak into the gyro cavity. So we do hermetically seal these two chambers. So we have the antechamber concept, which isolates the gyroscope chamber from the accelerometer chamber, and obviously from the CMOS itself. So targets for gyroscope, number one, high Q factor. Q factor obviously is defined as the, let's say, the quality of the used energy to provoke the motion of the signal. So minimum energy loss. Energy loss, and I note that here as the independent individual energy loss mechanism. Air damping is the number one cause. And this comes from the motion of the moving part in a compromised vacuum. And not the number, which is the ratio of the mean free path of the gas molecule to the MEMS critical dimension or gaps, will dictate this energy loss through air damping. And for that, as good vacuum as possible. Second one is thermoelastic damping. This is coupling for the elastic deformation and temperature. So as temperature and motion is happening, there is an energy loss from this thermoelastic damping into the silicon. Then anchor loss, so design dependent. The anchors are to be done in order to prevent this third mechanism of energy loss. And fourth one is really the material. The material with a point defect, dislocation, grain boundaries. In our MIDS, we use single crystal silicon. So when we look at that, the number one reason for poor Q factor is vacuum. Vacuum, at Q factor above 10,000, vacuum is below, let's say, 2-3 Pascal. This is very important. How do we maintain 2-3 Pascal over a 10 years life without a getter? How do we maintain Knudsen number below 10 when the line widths are in fact going toward 1 micron? The art is in the material sciences. So in this MIDI platform, air damping is a priority, and we avoid exposure of porous material to the cavity in order to avoid compromising vacuum. So no PECVD nitride, no TF, no PSG, no porous oxide exposed to the vacuum cavity. Getters are not in fact efficient to remove some of the gases which are generated by standard PVD and standard RIEHs, which are the helium backside cooling, the argon phosphoring, and some organic residue that may come from wear, surfactant, etc., from processing. So in this MIDI platform, we take great care of the source of the virtual leak, transpiration of material exposed to the inside of the cavity. The cavity being so small, we're talking here about 0.002 cubic millimeter. In order to maintain a pressure of about 1 Pascal for over 10 years, let's say 5 years, we're talking about molecules in rate of about 45 molecules per second injected into this cavity. It's not a lot. So we're talking here leak-up rate of 10 to minus 13 FCC per second. This is about, okay, let's say 100,000 times smaller as a leak that's what would detect a helium leak detector as per the standard military standard. So it's not a lot. And because it's not a lot, great care is taken in the design of this process flow. And that's what we offer. No getter, hermetically sealed, ultra-high vacuum compatible material exposed to tiny cavities. That's the principle for gyroscope. For accelerometer, you want the opposite. For accelerometer, you want to have an optimum air damping. So here's the schematic of this damped mass, okay? K being the, let's say, the spring constant of the anchors and the arms suspending the mass, and beta being the gas, the damping mechanism from the gas. So the natural frequency is square root, let's say, proportional to the constant of the arms divided by the suspended mass. Okay? And the amplitude coefficient, okay, is also related to mass. So depending on the design, you have a different mass, and depending on the mass, you have an optimum damping, which is the green curve here. So to a specific design, there is a specific damping pressure, and this needs to be optimized. But independently of this optimum pressure for optimum damping, there is a need to have gas inside the cavity, while gyros should have no gas inside the cavity. So we come with this anti-chamber concept. So we have here in the gyro cavity a good vacuum, and we have in the accelerometer cavity an optimized gas pressure. So basically in the course of that process flow, we generate the two cavities on the vacuum, and we leak one, and we plug one. All the contacts on the same side in order to allow wafer level integration to control ASIC and sensing readout ASIC. So here you see the throw silicon via, which is in fact isolated piece of silicon. So you should not see this as the through silicon via. This is a mechanical separation of the through silicon via here. Through silicon via is really a crystal, it's an aluminum connection, a contact connection, a single crystal N-type silicon, connected during this direct wafer bonding, and this is connecting to the various moving or fixed parts. Various connections isolated through these trenches, which are electrically isolated by a very thick, fat, 2-micron thick, in fact, thermal oxide for minimum parasitic capacitance. So here you see a couple of SEMs here showing the through silicon via tip, the through silicon via itself, okay, the gyro part, okay, some sub-assembly of accelerometers, etc., etc. So that's the concept of MIDI. In this structure, you only have crystalline silicon, thermally grown oxide, and very high temperature doped silicon exposed to very high temperature and machining. So here inside this vacuum, there is no porous material. There's nothing exposed to this vacuum cavity. And this vacuum cavity saw a very high temperature around 1100 degrees Celsius to make sure that this cavity remained ultra-high vacuum compatible. This is a cross-section in the second portion, okay, when my colleagues of CMC will discuss the access, we'll probably talk more, but this is basically the upper cavity, the upper substrate, the lower substrate, the through silicon via region, and this is inside the cavity, the sensor. So the sensor is this 30-micron deep portion of silicon vibrating and responding to the motion of the device. We have three substrates. We have let's say, a handle substrate. We call the base substrate, handle substrate. The device, which is the 30-micron thick substrate, which does all the magic of the motion. And then the TSV, which is the upper substrate to be able to execute the connections, the input connections and the output connections toward the ASIC. This is the base. 20-micron deep cavity. There's a typo here. This is 20-micron deep cavity. I apologize for that. This is 20-micron deep. 20-micron deep. This is 30-micron deep device. Okay, machine using what you will hear, MAS32. Then the 2-micron upper cavity, which is sensing the vertical motion. And then the through silicon via, which are 100 micron high, and then the output connection, which are redistribution layer of aluminum, okay, to the pads. So this is the 3D reconstruction. This is a cross-section which shows that this is not something which is a paperwork. This is a real device. This is a cross-section. These cross-sections are very difficult to do because you need to go right in the middle of through silicon via here. You have the connections on the top, the contact opening. You have the cavity, which is 2 micron high here. You have the 30 micron tall beam. It's in the region of the, let's say, some connection close to the anchor. This is the anchor here. There's a thermal oxide here. There's a silicon to silicon connection, and there's a connection to the out. So these kind of SEMs are very difficult to achieve because you need focused ion beam and surface preparation to hit where you want to hit. This is 5 micron by 100 micron, electrically isolated by 2 micron thermal oxide. So this is one typical SEM. Now, we manufacture these MIDI, okay, on 8-inch at C2MI, which is our research installation here in Beaumont. So C2MI is a class 1 infrastructure, in fact, because the wafers, the 8-inch wafer, are inside the Smith interface. So the Smith interface is, in fact, connecting all those bulkhead-mounted tools. Those tools are in a class 10 environment. So humans are in class 10 environment. Wafers are in class 1 Smith. The tools are in class 1000 chase area. These are the tools. So basically, for CMC, the development of prototypes are done in production equipment. And the reason is simple. When those devices work, we want to ramp in mass production. So at C2MI, only production-worthy equipment are installed. And all those equipment here, you do not see those mounted in the bulkhead. But basically, those are the Smith interface. There's Smith here, Smith here, Smith here, Smith here. So all those tools are bulkhead mounted. This is the back of the tool, and this is the front of the tool where humans operate the fabrication through those Smith interface. Design access, we will hear more in the second portion of today, but basically the process design kit from Teledyne DALSA are using the process parameter specification, design rule check deck, technology files for solid model generation. We use Synopsys and Cadence. The MIDIS solid model generation use Coventor. So we offer a truly representative 3D view of our design. Ready to design, multi-physics simulation, and I think the suite of software through CMC will also add over time. So this is, and I will let my colleagues of CMC talking about the support to that platform. But basically, for the Teledyne DALSA customer, which are coming directly to Teledyne DALSA, this is the suite of support to be able to verify the functionality of the 3D model of the device before we do manufacturing. What is important to keep in mind is this solid piece of silicon will go to 1100 degrees Celsius in the course of fabrication. So great care should be taken to simulate in 3D the expansion of the moving part in order to prevent those moving parts to collapse on the sidewall of those fixed parts. So these are very important modeling, thermal modeling that need to be done in order to prevent having a defective design that cannot go to those high temperatures. So shuttle runs will be done, multi-project wafers will be done through CMC, and we will hear in a few minutes how this will happen. Before I go, I will show you also what will happen with MIDI over time. So if you take your energy and your time to be able to design into MIDI, I want you to know where we're heading with MIDI for your future. So first, there will be a dimensional shrink of MIDI. What I see here in green is the device itself. The remaining is assembly and connection. So what you see here in green is really the moving portion. So this is what's moving in the gyro section and in the accelerometer region. The rest is connection. This is the through silicon via connection. This is the cavities to prevent stiction, process-induced stiction. And this is the plug to be able to have the two independent pressures. But what is important is the green section will shrink. And I will show you how it will shrink. Before we introduce formally MIDI, obviously we worked for some time on the MIDI. There was what we call a generation 1 MIDI, for which the line width and spacing were 2 microns. MIDI is offered at line width and spacing of 1.5 microns. So there is already, for this first offering of MIDI, a shrink compared to the first generation of what we did with this platform with line and space of 2 microns. But in the future, yet to be defined, yet to be announced, we'll shrink that to 1 micron. So those are the line and space, I will go back one page, of those features here. These are the moving, the combs, the sensing comb, the minimum dimension feature. Those features are shrinking, but what is kept constant is the aspect ratio of those features. When we used to be at 2 micron line and space, we used to have a moving membrane of 40 micron. Today we offer 1.5 line and space on a 30 micron deep device. In the future, as we'll shrink the 1 micron line and space, it will be on a 20 micron deep device. So this is what we're planning to do. Second thing is, future of MIDI will also go toward wafer level integration of MEMS wafer 8-inch to CMOS wafer 8-inch. So CMOS wafer, which are in fact generating the sensing ASIC, typically 250 nanometer, 180 nanometer, and 130 nanometer. When in fact those inertial sensors are targeting consumer electronic products, yield of the MEMS wafer is good and yield of the ASIC wafer is good. And by selecting the right node, 180, 250, or 130, we can adjust pitch. When the pitch of the MEMS and the pitch of the CMOS are matched, then these strategies are really shrinking the overall cost of the assembly, because the bill of material is really highly dictated by the various dicing, the various pick and place, the various wire bonding, and the substrate and the plastic molding to be able to have this co-chip being the MEMS and the CMOS. In modern time, this is evolving toward a wafer-level integration as to eliminate those extra costs which do not allow a very aggressive cost structure for these consumer electronic applications. So the first thing is use the doped silicon through silicon via, and the alignment power of the wafer aligners and bonder, which are well below 1 micron, and provoke this type of assembly. So this is the MIDIS platform. And this is a standard ASIC, 200 millimeter, 250, 180, 130 nanometer. It's not important. What is important is thin gold will be done by Teledyne DALSA on these standard ASIC, and the precision alignment and bonding of the thin gold to the UBM of MIDIS, and the mechanical bonding using those photo-definable polymer as replacement on underfill allows via those thin gold pad grid array and these nickel UBM with palladium and gold to do this, to be able to bond at wafer level the MEMS and the ASIC, and thin down from the MEMS side in order to reach the throw silicon via and provoke redistribution on the back of the MEMS, on the front of the MEMS, in fact. So MEMS and CMOS integration using low temperature polymer bonding as replacement of underfill, and thin gold soldering, back grinding and CMP of the wafer, the MEMS wafer, in order to reach those connections and do standard redistribution layer. Obviously, thin silver or thin silver copper, your choice, is not shown here. This can be done by many foundries in the world. Okay? And we only have one dicing here. We don't dice a MEMS, we don't dice an ASIC, we don't do pick and place of 2 substrates. This is on single dicing. So the system is, depending on the die size, which is matched between the MEMS and the ASIC, there are, depending on the application, between 500 and 50,000 system per 8-inch wafer. This is how we achieve low cost. With this first strategy where the connection to the outside world goes through the MEMS itself. So the ASIC pads are connected to the MEMS through this through silicon via, and it's on the redistribution of the MEMS that we connect to the printed circuit board. So you have a system in a cube here. Okay? The second approach is with the copper-based via last. By the way, I'm going back one page. This is ISDP-based via first, meaning we do the through silicon via before connecting to the CMOS. Okay? The second one is copper-based via last, wafer-level integration and MIDIS. In that case, we want to use the CMOS itself. We want to exit through the CMOS and not through the MEMS. For that, you still use the same aligner capability, well below 1 micron. But there are ways now to eliminate many input-output, many routing to the outside world by using a very tiny through silicon via, which is 5 micron diameter, to be able to connect directly to the various functions of the CMOS. The intent here is to input to the analog input of the ASIC directly the output of the MEMS in order to eliminate the parasitics and the connections and the input-output and the ESD protection diodes, etc., etc. All the things which are increasing signal and leaking the electron to ground. So this is to improve signal to noise, okay, and this is to eliminate wire bond, inductance, and RC effect to the pad. So using these 5 by 50 through silicon via, we can do now the following. Exactly the same MEMS, which are the MIDIS, and now the ASIC. And we would do on the ASIC now those 5 by 50 through silicon via copper base, and we would align, and by proper backgrinding of the ASIC as to reach now those copper-based through silicon via, we would do the redistribution, and now it's on the backside of the ASIC that we connect to the printed circuit board. So the intent of future of MIDI is to offer both cases. The ISDP base via first, MEMS to CMOS, where we would exit from the MEMS side, and the copper base via last, where we would exit from the backside of the CMOS. The MEMS is MIDI, the CMOS will be the CMOS of your choice, okay, from other foundries, and we have a list of 14 foundries. So, other future of MIDI, and it's about my last foil, okay, is we will want to integrate absolute pressure sensors, gyroscope, accelerometers, and pressure sensing on this membrane. So this will happen in the future. I am done. I hope it was not too long. I hope it was interesting. It shows you the present of MIDI, and it shows also you where we're heading with MIDI. So I'm done. I thank you, and I'm open to questions.
Okay, thank you very much, Luke, for the introduction of the MIDIS platform. Now I will continue the presentation. I'll talk about the MIDIS MPW service. So together with Teledyne DALSA, CMC is glad to provide the MIDIS MPW service. MPW means multi-project wafer, which means that CMC will gather all kinds of designs from different designers and put all the designs on a single wafer, single mask to make all the designs in one run. By this way, it can reduce the cost for each designer, so they will have their first prototype with low cost. First, let me talk about the TDSI MIDIS MPW service. Right now, the MIDIS process is scheduled 3 runs per year. The first run in 2014, the design submission date is March 12th, and the delivery date is July 31st. For most updated schedule, please check the fab schedule at the CMC website. Right now, there are 3 standard design dimensions: 4x4, 4x8, and 8x8 millimeter square. Depends on your requirement, you can choose from those standard size. If you really need larger dimensions, larger than 8x8 millimeter square, please contact CMC. The delivery quantity is 40 copies per design. You can order more designs if you need it. Just contact CMC before you do the reservation. Currently, the process design kit available is for Cadence, Covenantware, Edit for Tanner, and MEMS Pro. The Cadence kit right now have the layout and DRC function, as Luke mentioned earlier. Covenantware kit has a layout and 3D modeling function. And Tanner MEMS Pro Edit kit right now has a layout and DRC function. All those design kits will be available through CMC website in early November. Besides the MIDIS fabrication service, CMC also provides some additional service which can assist your design. If you don't have any CAD tools to make a design, CMC provides short-term CAD tool rental. So, for example, you can rent Cadence for 3 months to make your design and then get it into fabrication. We also have support some other tools like ANSYS and Covenantware, so you can do your simulation work. After the chip is fabricated, we provide packaging and assembly services. If you want to wire bond the chip to a standard package, like for example 68 PGA, we can help do it. We also provide a DIP package and QFP type package. We have standard test fixtures for those standard packages, so to assist your test. If you want to integrate the MIDIS die with CMOS die, we provide die bumping and flip chip services. If you want to attach a die to a stack to another one, or you want to just attach the die to a PCB board, we have the die stacking and die on board service. We have a design consultation and engineer support service to assist your design to make sure you have your design design ready for the fabrication quickly. After the chip is fabricated and packaged, if you need some test equipment, CMC Microsystems has a test equipment pool which you can rent the equipment for a short time for a test. We also have an online DRC server, so you can check the design rules for your design before the fabrication. In general, together with Teledyne DALSA, CMC will provide assistance for you from design to test and from prototyping to volume. This slide is how to get started to get access to the MIDIS technology. There's 4 simple steps. First, if you haven't signed the Teledyne DALSA NDA, you can download the TDSI NDA from the CMC website, finish the NDA, and then return to CMC. After the NDA is signed, you can download the design kit from CMC website, and then you can look into the process details and then start to prepare your design. When your design is almost ready, you can reserve your design space for the upcoming MPW round. There's 2 routines for Canadian academics. Please submit the RFMR application form to reserve your space. For industry and non-Canadian academics, please contact my colleague, Ray Filto. His email address is filto@cmc.ca to reserve the space, get the quotation. After the reservation is done, just prepare your design and then submit the design to CMC. After the submission, wait for 4 months, and then you will get your devices ready. If you have any technical questions, please feel free to contact me. My email is yang@cmc.ca. That's the end of the presentation for this webinar. So the next session is a Q&A. We will unmute everyone for questions, so you can ask the question via the telephone, or you can send your question to the operator. We will get your question answered.
The conference has been unmuted.
So everyone now is unmuted. So if you have questions, you can just speak to the phone.
Hello.
Yeah. Go ahead.
Hi. Yeah, my name is Li Shang. I'm calling from California. I wonder is that the presentation is available for download after the meeting?
Yes, the presentation will be recorded and put on our website this week, so you can go to our website to download and review the slides, and also
okay. Thank you.
No problem.
I have another question to Luke.
Yes, I'm hearing.
Hey, Luke, thanks a lot for the presentation. It's great. A quick question here. For accelerometer and gyros, right? Normally they have a lot of surface area. How do we prevent the in-use stiction?
How do we prevent what?
Stiction.
Stiction. Okay. Well, this is obviously a task which has been explored for many years. Stiction is really prevented. There's process-induced stiction, and there's in the field stiction. The most demanding one is really the process-induced stiction. At these scales, the surface tension of fluid and the surface conditions that prevent vertical and horizontal stiction. We have guidelines which are available to prevent the natural stiction by device. So work of adhesion and the length of the device, the stiffness of the arm, but basically we have the lower cavity, which is 20 micron, and the upper cavity, which is also 20 micron, in order to prevent the water-induced process-induced stiction. As for horizontal and vertical stiction, The vertical stiction is prevented by this 20-micron cavity. The horizontal stiction is prevented by a series of little horizontal bumpers that we call the belly buttons, if I'm not wrong, okay? And these are the type of features that are reducing the sidewall contact area in order to prevent horizontal stiction. So in the document, you should see, in the design kit, you should see ways to prevent horizontal stiction by the use of those very, very small features which are preventing horizontal stiction. Vertical stiction is prevented by the, let's say, the cavities. Now, again, I repeat, in the course of the fabrication, these devices will go to 1100 degrees Celsius. So in the thermal simulation using whatever you want to use, okay, we use Covento wear. In the thermal simulation, we have to verify, you have indeed to verify via your thermal simulation that the moving parts are not really expanding to a point where they will collapse and land on the fixed part of those features. Obviously, if they do land, since the process goes to 1100 degrees Celsius, there will be fusion, and this will be, in fact, seen as stiction.
Okay.
So did I answer your question?
Oh, yeah. So just one more quickly on top of that. Is that vapor treatment helpful to prevent in-use stiction? You know, normally I've heard people putting some hydrophobic film on top.
We have this technology. We use self-aligning monolayer anti-stiction coating, but you do understand that because we go to very high temperature, those fluorocarbon-based anti-stiction coating could not be used. In fact, they are not. Okay? When you look at the physics of stiction, again, surface roughness of the wall and work of adhesion and the physical surface area in contact and the spring stiffness, horizontal or vertical, are ways to prevent stiction by design. But they are not, there's no use of anti-stiction coating. We have anti-stiction coating. We have some self-aligning monolayer anti-stiction coating for hydrophobic, but we're not using this technology in this process flow.
Okay, thank you very much.
No problem.
So any other questions? If no other questions, I will do the wrap up. Again, if you have any more questions, feel free to send me the email. And thank you very much, Luke, for the presentation. And thank you all the attendees for listening to this webinar. Thank you very much, and have a good afternoon.
Thank you.
Thank you. Bye-bye.
Yep.